So, but do you have access to complete record for yesterday?
Yeah, I do. Yeah.
Okay, I think it should be okay. Yeah.
Yeah. So I can share my screen now. So don't worry if, yesterday it was a lot and I can understand. So basically what we want to do today is also just to continue from where we stopped, right? And I think the most important thing is for us to understand, standard, machine learning pipeline, in particular when it comes to development. So you want to build a model, and what does it look like? So already, and also last week, I laid emphasis on the fact that, standard machine learning pipelines, in particular for development, you want to, so this is how it looks like. First, you want to guess. I think it's just the idea. We want to guess because if you're training a model, you don't know, right? Because the idea is we want to, create models, right? And these models can be, we can just at the start, imagine we have our y-hat, whatever, you have beta 1, as usual, as we have always done, times some input plus your beta naught. Let's just take this for an example. And usually, X because X is your input, right? That is what we have been doing. And your beta 1 and the beta naught, they are the parameters of your model. You don't know. That's the problem. You don't know. And because we don't know, we want to train this, equation such that it finds the parameter beta 1 and beta naught that minimizes the loss between the predicted value and the exact value. So it's just basically, this forward, backward, right? And all along, you have seen how, we do these things, iteratively. You understand? We do a forward pass. For the first time, it's like guessing because this beta 1 and beta naught, they are randomly initialized. We don't know. And if indeed your y-hat, I'm just saying, if your y-hat, the original label is 2, that is our y is 2, right? And the question is, how do I ensure that if I have some input X that we don't know, right? In this case, let's assume that the X, the input is 6. I'm just assuming. However, we want to ensure that the output has to be Y. Because the input is X, we have to train the model to find beta 1 and beta naught such that once it carries out this linear operation, we have to get 2. And think about all the possibilities beta 1 and beta naught can take. Probably let me use 3. Just 3. And think about, without even training this model, you already know that you expect Y to be 3. Your output is 3 already, like your ground truth, which is your target, your label, the original value output is 3. And you want to train your input. Now I'm just using one number just to explain, right? Sometimes you have more than one feature. That's what we're talking about. You could have 2, 3, any number. And we want to train the model to guess or, to find the parameter beta 1 and beta 0 such that the result that it's going to predict will be very close to Y. Well, usually we don't work with one data point. We want to work with enough, quite a number because we cannot use just one data point to guess this value, right? Because we want to explore every possibility. That's the idea. But without even training this model, what comes to your mind? So can you guess a parameter beta 1 and beta naught that would ensure that this expression would give me 2? That is, 3. Now I changed it. So already I can just guess that beta 1 can be 0.5 and my beta naught can be 0. And what it means is that if I put 0.5 here as beta 1 and I put beta naught as 0 here, if I carry out this linear operation, already you know that your beta 1 is 0.5 and your beta naught is 0. Your input X is 6. Then this would surely give you what? 3, right? The Y hat is going to be 3. I mean, I'm just saying at the end of the day, probably we are just guessing. We have not even trained anything. We have not done any forward and backward thing. So, but because machine doesn't understand how to guess, right? For us, it's easy. We can say, okay, fine. I can just, take a look at it at one glance. I just find every combination of beta 1 and beta naught that can, output Y hat equals 3, because the original label is 3. I want to get close, as close to 3 as possible. Someone else can say, okay, no, what if I say beta 1 is, maybe you can look for something else. I can use maybe 0.2, right? 0.2, and the bias term can be, so already if we know that 0.2 times 6 is 1.2, right? So we look for the deficit, 1.2, that is, this has to be 1.8. Now, also, if I decide that, okay, I don't want my beta 1 to be 0.5, let me take it back. I just return it back, nothing more. So I don't want my beta 1 to be 0.5. I can say, okay, my beta 1 can be 0.2, and my beta naught is 1.8. Obviously, this would also work. It would give us 3, right? If I'm not mistaken, yeah, we have 1.2 and 1.8. That would give us 3, right? And for you, for us human, it's very easy for us to just guess, but in reality, you don't always have one data point. You have quite a number of data points, and you just want to learn patterns, right? You want to build a model that can do a prediction on some unseen data. And basically, this is what your model tries to predict, nothing more. So when they say the parameters of your models, they're just simply the weights, the biases and the weights, the biases, and I mean, just something like that. If we are working with just this kind of simple linear regression. And I explained the last time, when you work with models, you try to do a forward pass, backward pass, right? And yeah. So today, we would do a project called the MNIST dataset. And the MNIST dataset is just okay. So I can just go through I think it's okay. It's I don't have authorization. I thought I had it here. So we want to build a model that can predict, handwritten digits. So that's the idea. We want to build a neural network. So this is what the digits look like. And as you can see, the MNIST database is a large database of handwritten digits that is commonly used for training various image processing systems. So this project is, a very typical project in computer vision, because we are working with images as data. All along, we have been working with, numbers, like just, a kind of, we have been working with features, ordered data set, and, these features, they have meaning. Like in the case of the tumor, the benign and the malignant tumor, where each of these features actually represents something, right? But in case of image, for example, this kind of image, how do we interpret image? And well, images are just a bunch of numbers, pixel numbers, and these numbers just, this at every point, it's just like a grid. Think about this image as kind of grid, where each of the numbers in this grid represent the pixel values, and these pixel values, just tells us the intensity. I think yesterday we talked about it also in the slide, where you have for example, in this 5, all this white region would have higher intensity, right? And if it's an 8-bit image, you have them to like 255. So if you read this kind of image in Python or in any other language, you'll find out that around this point, this white regions, you see numbers, and the dark regions will just be 0. So today our task is to predict. Okay. Can we mute this? Okay, so our goal is to build a model such that when we feed this image into the model would be able to predict the number, because this is handwritten, right? Good. So now let's start. The data, we can, of course, we import our libraries, Torch, right? Because we are working with PyTorch. We import also the neural network module. There is also the optimizer I talked about. I didn't also stretch much about the optimizer, but I'll talk about it also when we proceed. There is also Torch Vision. Is also, there are also libraries in PyTorch, in Torch. We have a lot of, functionalities, like the data sets. I'll talk about that. Transforms, if you're working with image, usually you want to transform your image, especially when you have image, when you have PIL images, PIL image, pillow. When you read an image, you want to, because we are not working with NumPy or any other kind of image data type. We want to transform it to tensor because we are working with. We want to transform it to touch tensor because we are working with tensor we are working with PyTorch, touch tensor rather. So if you are working with TensorFlow, then you have to also try to work. You have to be consistent. Remember yesterday we tried to multiply a NumPy array with touch tensor, and it threw an error. So data loader is just it's just an effective way to to load our data, right? I'll talk about that also. Our matplotlib, and also we want to find the accuracy and NumPy. So we quickly execute this. Let me, so that we can see. Now, so the next thing is we want to set a seed such that we ensure that our codes are can be reproduced. So we set the seed if it's in Torch or NumPy, or if you are running on CUDA. Okay, that reminds me, I think I have to activate my runtime. Yesterday I talked about if you are working with images or even large data sets, I can assure you that you want to work want to train your models on GPUs. And like I said yesterday, graphics processing unit, they help to accelerate training and it runs it runs the forward backward pass in parallel, and it makes the training faster. And that is what we want. So now, what do we have here? This data set we imported from here, from the Torch Vision library. The MNIST data set is also there, is inbuilt. You can, if you want to download it, it's fine also. You can download it from Kaggle. There are lots of places where you can download the MNIST data set, like Kaggle. You can decide to download it locally on your machine. It doesn't matter, like here now, it's just 23 megabyte, sorry. And it contains 60,000 training examples. That is, we have 60,000 images, and we have 10,000 test examples. Good. So now you just call the dataset.mnist, and of course you want to get the training set. This is our training set. Remember, we want to train the model on our training set, so you have to put this to true. And the transform equals transform here. Here we define our transform because the images are not in touch tensor. Of course, you have to, transform it to tensor. Remember, we have to be consistent because we are working in, in PyTorch. And also we want to normalize. Remember, I think yesterday and also last week, we talked about, normalizing our, feature because we want to, we want to standardize it. We want to center our, this image, this feature, around mean 0, around the mean and standard deviation, something like that. So we also call our test set, which is what we would use to test the performance of our model. What you see here is just, where the path, you specify the path you want to download the image. Okay, and good. So what is this? I'm going to explain this, but first let me run what we have here. And you see downloads, like it's just quickly download, right? And before I run this code, so let's see our training set. Let's just print, let's print the shape of our training set. As you can see, okay, it doesn't have the attribute shape. Okay, let's see. Okay, because it has training and, okay, it's a tuple of the image and the label. Okay, let's just print what we have here. Yeah, so what we see here is, is a kind of, is a method, you see. So, yeah, so what we have here, so I'm going to explain. So what you have here is, you have the image, as you can see, as tensors, but it's a tuple. It's a tuple of, so what you see here, so these are the pixel numbers, I was talking about, right? When you read the image, it brings some numbers, but you find this negative because we have normalized it. Remember, when you normalize it, you get, negatives because of the, formula we use to standardize the data, the numbers. And as you can see here, this is the feature, this is the label. What this means is that this is number 0. We are going to show it in a plot. But what we find here is just, for each training example, it's a tuple of the image itself and the label. So now, if I put 0, because remember, you can access the first element of a tuple with its index. So this is the image, as you can see, and the label, we just use 1 because it's in the second index. And you see, this is number 0. Now, what is data loader? Data loader, is just, usually when you have data set, remember, you have them, as, how can I say, they are individual, examples. For example, they are individual, training examples. So think about when we work with data frame, what do you have? You have your data frame, 1, 2, 3, 4, 5, 6, 7. And, you always have this, you have some, some feature, X, Y, Z. And, you have these individual samples up to 8 in this case. But the question is, how can we, structure our data set in a way that when we are trying to access our data, we won't access them individually. For example, you can only want to find an efficient way to load our data set, in batches, right? In batches. And usually it's the case that when you work with, batches like 8 at a time, or 16 or 32 or whatever, I think during the backward, the back propagation, our model tends to, during the optimization, it tends to gradually, approach this, local minimum. And so, for example, if I want to, we have 12 examples here. I can load this.
Sorry, can I stop you? I'm sorry.
Yeah.
Can we have the link to this notebook? I don't know.
Yes, I would send it to you after. So after this class, because I have to explain.
Okay, no problem.
Yeah, thanks. So thanks. So we have n equals 12. That's our we have 12 training examples. And what if I decide to, for each iteration, right, I want to load 6 example once, right? So what you have is we have so I want to load 6 image at the first, like at every iteration, the second one 6. So what it means is that I'm going to have 2 batch here, 2 batches, because in the first batch we have 6. So this will be the first batch. First batch, and this will be the second batch. So what would happen is during the forward pass, in the forward pass, you want to iterate all through the through the training examples, right? You want to iterate through 1 to 12, and think about, do I really have to iterate at every individual example, right? And there's what we call stochastic gradient descent. So of course there are research that shows that when you try to optimize your model at using each individual training example, there is this noise, right? When we the loss would be very unstable. So it's better to pick these training examples in batches, right? So now in the first during the iteration, during the first forward pass, it's going to grab these 6 once, and that is what you find there, like as the first batch. So the first batch would contain 6 examples, and the second batch will contain the next 6, right? So in one pass, we only need to iterate twice to complete one forward pass, right? Because a forward pass means you have to train all the training examples. And how do you achieve that? So we want to put them in batches. So in one forward pass, we can call them in batches, right? So the first batch would be 6 examples, the second would be 6 examples, and we are done, right? And if you have, like, let's say 100 examples here, and you're working with, let's say, 6 batch, then it means you are going to have 100 divided by 6, right? Number of batches. And the last batch, if it's not up to 6, then it's just going to exhaust the remaining. So that is exactly what this data loader is doing. Our training set is just the set of training examples, which is 60,000. And we put a batch size of 64, right? So what it means is that for each during the forward pass, our model will be grabbing 64 images, right? And imagine we have 60,000 training examples, then the number of batches we are going to have would be 938, because the last batch would not be up to 64. This is because, of course, it doesn't have to be exact division, something like that. So think about it like that. So what it means is that we have 60,000 divided by 64. As you can see, we would have 937.5. It means the last, in total, we are going to have 938, but the last one would not be up to 64, right? Good. So now we have our train loader. That's what we call the loader, and the validation loader, the test set. Good. So now let us visualize our image, because I've just been talking, let us see what this image, so this simple, I just want to plot 20 random images from our data set. And yeah, what this is just doing, I create a subplot of 5 by 4, and this I here just is the number of image I want to look through, and I want to grab 20. So I'm going to have 5 by 4. Of course, it has to be it has to rhyme. If you're using 25, then 5 by 5. And so I just randomly sample an index because I have 60,000 training sets, right? I just want to randomly sample 20 images, right? And I can just use my np random.int. So this would sample just one number between 1 and 60,000. And, you know, I can remember our training set, as I showed us here, is a tuple. So when you access the first one, it's a tuple, right? So as you can see, we are grabbing the image and the label, because for a tuple, you can easily, you can easily grab, all the items of a tuple, right, at once. Good. So we have the image, we have the label, and we can just, plot it. Quickly, we see the images, 1, 1, 3, 3, and these are handwritten, digits. As you can see, 6, 6. So we want to train our model such that once we feed in an handwritten digit, an image of a handwritten digit, then the model has to predict, the number, right? And for example, if you write 3 and we feed it into the model, we expect our model to predict 3, 0, 0, 6, 6. And we have 60,000 of this. And as usual, what is our model pipeline? We want to move forward, we do a random guess. Here, we do a back propagation, which is the gradient. We adjust the weight. We go again. We do the same thing. And, it's a kind of loop. It's a feedback thing. We go forward and backward. And think about, so, yeah, that's just basically the pipeline. So now let's, just try to remind us about probability distribution. So, and this is basically what we'll be working with. Because we are classifying this image, we are classifying these, all of these images. I think we have 10 classes because from 0 to 9 is 10. We have 10 classes, 10 classes. And what we want our model to do is to output some kind of probability distribution. And the probability distribution tells us how likely is it that an image belongs to a particular class. Now, take for example, I have this color, and think about this color here as the, the color represent the classes, right? So different classes we are, we want to, group an image or whatever. And in the prediction, one of this color must be the correct answer. So we have blue, orange, green, yellow, red. This is not the case of multi-class problem. A color can only belong to one of these class. So a blue can never be orange, right? And we want our model to predict the color of anything, just anything, right? And what our model would do is to output a kind of probability distribution. Now, looking at this, this diagram here, our model is predicting that yellow has 38%. Has a probability of 0.38. So, and if you compare it with others, yellow seem to have the highest probability. And what it means is that we want to take yellow. That means yellow has to be the correct prediction, right? And this is basically what we are going to be, doing today. What we would do is, when we feed in an image into the network, our neural network, it has to predict 10. We are going to get a probability distribution like this for 10 numbers. That is, we would have 0, 1, 2, 3, 4, up to 9. And for each of these output, we would have probabilities assigned to them. And the highest probability, the number with the highest probability would be our prediction. Okay, now, good. So for the loss function, all along we have been working with, this binary cross entropy, and that is just very, very specific to binary problem, to binary class problem. Well, this is not a binary class problem. We have 0 to 9. It's more than binary, right? It's a So it's a non-binary class problem. So that is to say, we have more than 2 classes. Now, usually this is the cross entropy loss, and this is what we would use for our prediction. And I would like to remind us, the last time we worked with this, when we worked with this, when we want to compute the loss, you know, this has to be mutually exclusive, at least for the problems we have been solving. You know, when y is 0, this term would cancel out. And what you have is this. Now, what it means is that if my y is 0, this automatically would, you know, would just vanish, because 0 times log p is 0. And if we replace y with 0 here, we will just have 1 times log 1 minus p. And the p happens to be the prediction. So if we are predicting a value to be 0, that is, if we assume that the probability, you know, the value assigned to that class is 0, then what we are going to have here is 1 minus 0. So in general, what we would always have is we just want to get close to 1, because for any probability distribution, 1 has to be the highest you know, probability for any for any probability distribution. So what it means is that you cannot have more than 1. You cannot have a probability more than 1. So the goal is to always ensure that whatever we are predicting is just close to 1. And, you know, it's more or less, we don't want to be far away, right, from, from the maximum possible value, which is 1. And we just find out that this, what we have been working with is just a special case of this, cross entropy formula. And if you read through the slide, I explained, but yeah, for this problem, because we are doing multi-class problem. I mean, it's not a binary problem, rather, yeah. So a non-binary classification problem. We have to use the most general form, and the most general form will be that what our model is going to output will just be the probability. So we just want to ensure that we pay more, we put more preference. So we put more preference on the index of the class we are trying to predict, right? And I'm going to explain. This y always, we would always assume would be 1. Yeah, would be 1. I'm also going to explain. So what it means is that, just as I've illustrated here, think about this binary case. I mean, even though you are predicting 0 or 1, if you have y to be 0, I said this term would vanish. What you'd have here is just 1, right? And the 1 here just automatically means, we just want to, always ensure that the probability or, assigned to that prediction should be 1 always. And now, if our p is, say, 0 also, we are also going to be very close to 1. And in the end, we are also, trying to pay more, want to give more preference to the, predicted value, which should be close to 1. And also, if our y is 1, you know that here would be 0. This term will just vanish. And we are, and we are back to, where we are back to where we started from. And this would be 1. This would, of course, the probability would want it to be close to 1. And if you remember the logarithm, the negative log curve, when your x is 1, the value, the corresponding y value is always low. So we want to, penalize the loss. We want to decrease the loss. And when we talk about backpropagation, right, we want to reduce the loss. That is the whole idea, right? And of course, previously I've shown that during the forward pass and the backward, we want to ensure that the loss is decreasing. Well, that is, in the case of, in a simple linear regression, it's very easy to visualize, right? Because, it's not in high dimension. But when we are working with neural network, we have more than, one parameter. like could be up to thousands, millions, billions, right? And, someone asked the question in the group, is gradient descent also the same as, so there is no closed form solution for problems like this. And, what we want to do is to ensure that, if we are starting, think about you're on a hill and you want to, your loss, which is the loss in this case, you want to ensure that, because there are lots of, it's a kind of noisy, space. It's a high dimensional space. I just want to get to the bottom, to the, to the minimum, to the global minimum, right? And you begin to move, right? As the parameters are, updating, begin to move, and we want to get to that global minimum. But there is always a problem when you're working with there's always a problem when, when you're working with in high dimension, because think about this hill. If you're very, if you're very familiar with hiking, you find out that when someone might just get stuck here. Think about you are here, right? And it looks like you have settled down somewhere. It looks like that is the minimum, but no, it's just a local minimum, right? And if you're very familiar with also stability or things like that, we don't want local minimum. We want the global minimum. Global minimum means that is the last we can go, and that is the most, that is the lowest point in this hill, and and that is where the optimizer comes. That is where the the optimizer thing come into play. We don't want to get stuck here, because imagine you are just here. Your model cannot get out from here. You cannot get out from this. This kind of, you are trapped in this place. Whereas you have to be here if this place is actually the global minimum. And that is where the idea of momentum comes in. We want to ask if it's just like if you roll a ball, let's say you are in you are here, you roll a ball up, the ball would surely come down, right? And the question is, how much of momentum can I push the ball such that is it possible that the ball can get out from this local minimum and just continue to descend? And you find that in standard optimization technique, we want to just ensure that if we nudge this, if imagine I'm stuck here now, if I nudge this particular, let's say this individual, let's say starts from here and just gets stuck here. If I push this individual, is it possible that this individual can get out from this, from this local minimum and continue to descend, right? So now let us build our first neural network, right? And yesterday I explained how we can build our neural network. The RNN.linear all along we have been initializing weight ourselves. We don't want to do that ourselves, right? And if you look at this, I missed it. Now, if you look at this, I also explained this yesterday, if you remember, that this is just the linear operation we know, X times A transpose T. X is the input data, the feature, or the input rather, and A is the weight, right? And we have to transpose the weight so that the matrix multiplication will be possible. And we have the bias. And what we just need to do is we want to put the number of features, right? And the output. And when we are working with neural network, remember, we want to sorry, I didn't put the image. I can just Google neural network. And so I would also explain. Yeah, I think I like this image. So what we want to do is we want to, okay, it's loaded. So yeah, sorry. So I just want to explain again, what, what this network actually looks like. So all along, this is what we have always been implementing, simple linear regression. You have your input, you have the weight, and you have the output, straightforward. Now in neural network, like I explained yesterday, we don't want to just work with one, node. We want multiple nodes that can be, I didn't find the image. Okay, this is the image. Yeah, so what we want to do now is, imagine this is the input, and I want to create this hidden layer, like I explained yesterday. So think about this These are the 3 hidden layers. Now, what PyTorch would expect is, remember, so 1, 2, 3, 4, 5. The input is 5, right? Now, because the input is 5, we have to put 5 here. Now, remember, our image, this image is 28 by 28. I should have just, you know, and I should have just, I will print out the shape so that you can see it's 28. It's 28 by 28, right? You know, it's a touch tensor, 28 by 28. So it's a, you know, it's a grayscale image, which is black and white. And, you know, the height is 28. The width is 28, as you can see here, 28 by 28, right? And because we are building a neural network like this, now the images, our images, they are not, you know, they are grid-like, they are in grid, like, you know, like I mentioned. So they are grid-like. So it's a 2-dimensional thing, right? In this case, 28 by 28. So the one there is just a channel, so it doesn't matter because it's just a grayscale. Now, how can I feed in a 28 by 28 image in just, you know, in this kind of, in this kind of scenario? Because this doesn't look like a grid. It doesn't look like, you know, a 2-dimensional something. It's just it's just a vector, right? Like in this case, 1, 2, 3, 4, 5. So think about, so let's just assume this input is, okay, so yeah, this is 5 rather. And what we want to do is, how do we convert our image? How do we flatten our image such that, you know, because it's a linear layer, such that, you know, the multiplication can be possible. So, I mean, the network itself can be possible. So what we want to do is, because our input has to be in, you know, it has to be a 1 row, I mean, it has to be a column or row vector, depends on how you arrange it. So we just want it to be a long, you know, we don't want it to be a grid. We just want to stretch it. And I explained yesterday, what we are going to do is that that 28 by 28, you know, we are going to flatten it. And I explained that if you have 28 by 28, you would have 784. So what we have just done is we are flattening the image. So basically what we are just doing is, imagine this is 28 by 28. We pick the first 28 row. We pick the second 28 row. We stack it together up to this point. So we just, you know, we stretch it, something like that. And in the end, we'll just be having 784. So, and that 784 is what you see here in our first input, because it has to correspond. We are building just, you know, a neural network, an artificial neural network. And, you know, we want to pass it as a, you know, as a linear operation. We want to carry out a linear operation, right? Linear operation is not possible on grid-like, you know, data. It's not. And so that is why we put 784. So don't be surprised. The 784 is because of we are flattening the image 28 by 28 pixels. And now the next thing is, how many nodes do we want our first hidden layer to be? Now this is our so not the first hidden layer, which is this point. Well, it's a hyperparameter that, you know, you can try to experiment. However, depends also the complexity of the problem. But, you know, what I've just done here is to, you know, the first hidden layer has 256 neurons. So what it means is that I have 256 of these circuits, of these nodes. Good. And now, what is the second hidden layer? The second hidden layer would be 128. Remember, each of these this NN.linear can only, you know, create one layer, right? And for the second layer, remember I said the input of this, I mean, this first hidden layer would serve as input, to the second hidden layer, because, it's a network. Just look at everything is just propagating, in this forward, so this, our image that we flatten is an input to the first hidden layer. The result of the first hidden layer would be the input to the second hidden layer. The result of the second hidden layer would be input to the third hidden layer. And the result of the third hidden layer would be the input to our output layer, which is where the prediction will take place. So now, our input is 784. Our first hidden layer is 256. Now, for the second hidden layer, we have to, put the dimension have to be the same, because remember, I said the input, the output of one hidden layer has to be the input of another hidden layer. So this 256 would be the input, because the output here is 256. And here we create the second, hidden layer. Now, for the third hidden layer, remember, the output here will now be the input here. Then we have 64. So what it means is that we are creating 256, 128, 64, 64, and this is the output 10. So here we have one hidden layer, two hidden layer, three hidden layer, and just the output. Remember, this doesn't count because the output of the previous hidden layer has to be the input of the next layer. So this is the input. This is the first hidden layer, 256 neurons. This is the second hidden layer. This is the third, and this is the output. So here we have three hidden layers. Good. Now, this forward method, what it does is, when we call this class, net, and we, it works like a kind of call method. Well, it's not like, a function rather, but what we do is that it expects, it works like it works like a function, right? Which takes in the image. So this X here would be our image, because when we call our class module, this is just our network. So first we want to reshape it. Remember, we cannot work with 28 by 28. And let me just give an example. If I say torch.rand n 28 by 28. So let's print x.shape. So what you have is 28 by 28, right? But you don't want to work with 28 by 28. We want to flatten it. So we can just, what we can do is, there is, also it's the view is also another functionality in Torch. You can use that, you can reshape your image, right? You can reshape your image. And so when you reshape your, in a way, we can flatten it. So what we can do is we can view it to be 784 by 1. So if we print s.shape, so what we see now is that because the original image is 28 by 28 already, we know, but I want to view it as a 784, just like a vector of 784 pixels, right? We flatten it, and this is what the view would do, right? Yeah, basically that is what we are just doing here, right? And what this -1 is just doing is, okay, just by default, we don't have to specify, we don't have to specify whatever, we don't have to specify, we don't have to, yeah. So when we view x.shape, then we have, yeah, -1. Okay. Yes, so this would flatten. Okay, all right, so sorry. Yes, so what we are doing now is, yeah, so because we have, it's a one-channel image, so what PyTorch will do is, x.shape.0, because we are working with one channel, and of course PyTorch expects, we want it to be, we want the batch the channel and whatever. So this x.shape.0 is this one here. And this -1 here just means tell PyTorch, please, you can just do the remaining. You don't have to specify, right? And here we would have 1 by 784. So this is just basically what we have. So what this means is that we have one training example and we have 784 vector. But imagine we have, yeah, sorry, I'm going to explain. So imagine we have 19 examples. It's going to be 19 by 784. So usually what PyTorch expects, so if PyTorch, so in this forward pass, what it expects, it's the batch, the channel, the height, and the width. So by standard, always keep in mind that this is what PyTorch would always expect. And remember our batch size is 64. We specified it, right? The channel is 1, right? The height is, 28, the width is 28. But we don't want to work with grid-like image. So we want to shrink this height and width as to vector, just 784. So when we call the view, the x.shape.0, we just specify the number of batches. The number of images in one batch. And so we want to keep the batch because we want to ensure that the number of examples should not change. What we just want to ensure is every other thing should be squashed should be flattened. And that is why we specify -1. -1 would do the remaining calculation. But if you are very sure, if you type 784, it's still going to work because you know that 28 by 28 times 28 is 784. But sometimes you might not always be sure. And if you make a mistake and you put 786, you would get an error because this operation cannot be possible. That you want to keep this dimension you want to convert this to 786. So always it's better you use -1, then Python does the rest. And what we just want to do now is to, we call our first linear layer here. We wrap it around our input, our flattened input, and we call the ReLU, right? Remember it's the activation function, and the activation function just tells us, if we are going to, activate a node or not, right? Yes. So I'm still going to share the, the video. There are a lot of, activation function, and you can also read about them. And this is rectified linear unit, and what it's just going to do is that if the output here after the first layer, that is the linear operation, if it's 0, ReLU will just kill the node. It will kill the neuron, right? Remember, yesterday I showed, I'm going to also send the script. You would see that the ReLU activation function will take the max between 0 and this output. So if this output is 0, if this output is 0, if the output is negative or 0, the node is just the node would be dead because ReLU will just output 0, and 0 times, when we take the 0 to the next layer, it's just going to be 0. But if this linear operation is positive, of course, it's a positive number and 0, the maximum is the positive number. So, and then ReLU, the activation function would activate that neuron. So let's run our code. Now we call our neural network, right? This is the class net. We call our cross entropy loss. So the cross entropy loss is what you see here. However, we have to note that the cross entropy loss applies the softmax function because this is our output here. The model would output logits, just raw logits. And the logits are just those numbers between -infinity and infinity. And remember, we don't want to work with, we want to work with probabilities, right? And so in this cross entropy, you can also, I'm still going to talk about that if there is time. If you check the documentation, you find out that in the cross entropy loss, it applies this softmax. So softmax is a more generalized form of sigmoid. And after it applies the softmax, then it's going to calculate the loss. So the cross entropy loss is just simply the negative, I think there should be and there should be an average, but of course, okay, no, this is just for one class. So for other class, if you have more than one training example, then you have to average this loss, right? Because you want to find the average. So yeah, the output here, they are just raw logits, and the cross entropy loss would apply. I'm going to explain that also. So let's just assume, I'm really going to be fast with this. So assume that we have some logits. So in this case, our model will output some logit. Tensor. Yeah, see, just to give us an idea of 2.0, let's say these are just logits, minus 1.0, let's say 0.1. I want to create two examples, minus 1.0, minus 2.0, 0.1. And yeah, so keep in mind that this is just, batch size. Remember, I'm working with the batch size of 2 because this is 2 training example, and the number of classes will just be 3 because for each of the example, we will predict, 3, the output node is 3. Now, good. So, but if we print this logit, it doesn't make sense because these logits, they are, they are just, we have negative, positive, but we don't want to work with these, right? We want to work with probabilities. That is the, that is the idea. And so how can we convert this to probability? Now, if you look at the logarithm, the exponential, the exponential function, is, takes values between minus infinity and infinity, right? And if we have minus infinity, we will have the corresponding y to be 0. And if we have, x to be positive infinity, then we would have, the number, the equivalent number would tend to infinity. So that is what we want to do. First of all, we want to interpret this as count, not just raw logits like this. And when I mean count, remember in high school, if they tell you if you have if you have 4 males in a class and we have, let's say 9 females in a class, and someone asks you what is the probability. So if I pick someone at random, what is the probability it's going to be male? Already you know that the answer is just male plus female, right? I mean, that is what you would always do, right? And it's very straightforward because the 4 here is count. So it's not acting like a count. So it's the count. So if we know this count, then we can just easily, find the probability, right? But in this case, these are not counts, right? They are logits, and they are numbers between minus infinity and infinity. We want to ensure that we have numbers that are greater than or equal to 0, at least counting numbers, right? And what we can do is, since the exponential curve takes values between minus infinity, it squishes the value between 0 and infinity. That is between 0. If x is minus infinity, we have 0. If x is positive infinity, we have plus infinity. So the exponential function simply would just squish these logits between 0 and positive infinity. Now, so let us now convert it to count. So we want to convert the logits to count. So the logits, we just take the exponent, right? So we can just, if we print the count now. So now what you would just see now is that these numbers, this 2 minus 1 is now, 7, blah, blah, blah. So this makes sense, right? Because they are counting numbers, right? They are positive numbers. Now we are now back, we are now in this, scenario, right? And what we now want to do is, now that we know the count, it is very easy. It is very straightforward for us to calculate, to get the probabilities of each, because this is one training example, and this is another training example, right? So remember what we did here, we sum male plus female, right? Because we want to divide each of these male, female by the sum, right? So what we can do now is to, we want to sum this, because this is one training example, right? Because this is one training example, and we have the first class, second class, the third class. In the first training example, in the second training example, we have the first class, second class, we have the third class. So what we have to ensure that we have to sum this, then we now divide this individual class by the sum of this, right? So how do we sum? So it's very easy. We can, I think we can just do count dot sum, and we have to specify the dimension. If you look at, let us print the count dot shape. It's very important to know the kind of shape, the shape. So if you print this, you will see 2 by 3, right? So what it means is that we have 2 training examples and 3 classes each, just as I've specified here. Batch size of 2 and number of classes to be 3. So what I want to do is I want to sum across, I want to sum across the rows, right? I want to sum across the rows. And in doing that, I have to sum across this dimension 1. Because what it means is that if I sum across this dimension 1, what I've done is this sum is just this here. And this guy is this sum here. So it makes sense. Now I've gotten my sum. What do I have to do? I will take this, divide by this, take this, divide by this, take this, divide by this. So that is for the first training example, right? Then for the second training example, this divided by this divided by this. Now, let us try to get our probability, because it's the probability we want. We don't want count or whatever. So our probability would be, remember, we have gotten our count, then divided by the sum. But this will throw an error, and I will tell you why. Oh, okay, sorry, count. Here, now we want to print our probability. Just as I explained, each of the classes we divide, it will throw an error. Yes, so this is because it says that the size of a tensor 3 must match the size of tensor A, dimension 3, must match tensor B2 at non-singleton dimension 1. Now, let us print the shape of this sum, of this sum dot shape. Now, when we print the sum, of course, because we are summing along the column, along the rows, this dimension vanishes, right? Yeah, because we are summing just along the rows. So this will just give us one number, which is this and this. And now when we are trying to divide, we want our count here is 2 by 3. We want to divide 2 by 3 by 2. It's not going to work because they have different dimensions, because this is 2 dimension and this is 1 dimension. And as you can see, it complains that here is 3 and this one here is 2. And this is because when you perform this operation, PyTorch will try to take the last dimension of this and divide with, with the last dimension of this. But the problem here is that we cannot do this because we have this to be two dimension and we have this to be 1 dimension. So here, when we sum it, we want to keep the dimension. We want to keep the dimension. So by default, it is false. So when we keep the dimension, it is now 2 by 1. Now, when we carry out this operation, PyTorch is going to broadcast. It's going to do a broadcast. So what it means is that we have 2 by 1. So what it will do is it will take this, it's going to duplicate this thrice, 3 times. So that's broadcasting. It takes this, divides by this, takes this, divide by this, takes this, divide by this. And this is possible because the dimension is now, so we have 2 by 1 and 2 by 3. So PyTorch is going to duplicate this 1 3 times across the rows, right? It's going to duplicate it 3 times across the column. So now when we do this, the probability is now, so this is now the probability we need, right? So yeah, that is just for an example. But usually we don't want to, always, write this code. So there is this functionality, torch.functional. I mean, usually you would want to, use inbuilt method. And what we can just do once is to find the probability. We don't even have to do all of this we are doing, just call the f.softmax. Remember I said softmax would, convert the, convert it to probability. So if we feed in our raw logit, not even, I mean, the raw logit. So if we feed it into this place and we print our probability, and you will just see that the result, softmax. Did I run this? Oh, okay, torch.nn, sorry. Yes, so now you see this guy here is just the same here. Well, because this, we just, we wrote it with our hands, right? And yeah, so it doesn't, yeah, it's just the same. So all of this conversion to, take the exponent and yeah, it's just the same. So basically this is what so now when I call this cross entropy, the cross entropy, remember it calculates the loss. However, because the output of our model are raw logits, it will first perform this softmax, then it calculates the loss. And the loss is already what I've explained here. Good. So now we can just proceed. So we define our optimizer, Adam optimizer, the learning rate already. Remember, we need a learning rate for that model for the weight update, and the parameters, because the parameters are the weight, right? And we want to ensure that these weights, are kind of optimized in a way that, because during the gradient descent, we want to ensure that we are the global minimum. And our device is CUDA because we are running on GPU, right? And if you print device, we are going to see that it's GPU. Now, so you can see it's CUDA. So we take our model, so we move our model from CPU to GPU. So you just use PyTorch as this .to, then to CUDA. So now we have moved from CPU to GPU. And as you can see, our model architecture, I try to print out our model here. Did I try to print it here somehow? The model, print device, model. Okay, yeah, here. So this part prints the model. So this is our architecture. And remember the 784, 256, the bias is true. So it means that during initialization, we have the bias term, and this is just what we have. Now, yeah, yeah, so I wrote this, so, well, you don't have to worry much because everything I've talked about, you will find it here. And now just to explain, we have this class called model trainer, section in a way that we have a train model, a method called the train model. What it does is to set the model to training mode and compute the loss and output. We have the validation because we want to test the model on unseen data. And we have the accuracy. We want to know how many images this model gets correctly. And there's what we call early stopping. We don't want the model to run forever. And probably we want to always pick the model with the best loss. So what we want to do is we want to stop the model if we notice that the loss is no longer improving. Because if you are iterating, if you are doing this iteration forward, backward, at some point your model might not even be improving, and you don't want to. And since this forward back is always overwriting, the last, it would always overwrite the last, parameter. We always want to checkpoint, like, we want to keep track of that model that has the best performance so that we don't lose it. And that is what we call early stopping. Once we notice, we keep track. We set a patience to maybe we want to wait 5 times, and this is what you call patience. So it's just like, okay, how much patience do you need, for you to stop the model if it's not improving. And that is what patient is, patient. Here we initialize our criterion, which is our, cross entropy, our optimizer, our device, and we just set a best loss to 0, right? We initialize. And we want to also count the epochs without improvement. Epoch just means iteration. And for the training model, we set our model to training mode because PyTorch, in a way, tries to recognize if you are in a training mode or evaluation mode. During evaluation mode, we don't want to update the weight, right? It's only during training. So you have to be careful. Otherwise, it's going to accumulate, these gradients. And the data, the target, already, we have gotten from our data. Remember, our data is the training set, and the target would be the labels, right? And we want to clear the gradient because yesterday when I talked about when, in the optimizer stores gradients, right? So, and it can be very memory consuming. So we want to always, after the update, we just zero everything. And, the output will just be, we call our model, and the model is just, this is our neural network. It's going to output this X, right? Which are logits. And remember, our data is our image, the images. And once it outputs, the next thing is to calculate the loss, right? We want to do a backward propagation. And the criterion, we want to calculate the loss. So remember, the criterion will convert that logic to probability and find the loss. That is, take the negative log of the prediction, right? Because we also need the target so as to serve as a kind of guidance to guide the model. And we do the loss.backward. We did this yesterday, and you know what this will do? It will compute the gradient, right? For each of the parameters. And what we want to do is to update the gradient. Remember, yesterday we were using the gradient. I think the formula, right? If we say like W old, like for the weight equals to, W new, if you remember, would be W old minus, the learning rate times, the derivative, remember, the gradients, right? But we don't want to do this, right? So PyTorch, we can just call the dot step. Dot step, we just automatically, do this for us, and we are fine. And that's just it. And then we return the loss, right? We want to also keep track of the loss because we want to use that as as a means, to track our model. And that's just it. The validation is also the same. The only difference is that we have to set this to valuation mode. Remember, because during training, it has to do the weight update. But in evaluation, we are not doing any weight update. So we have to set it to evaluation mode. And also, there is no loss.backward because during validating, like when we are testing the model on seen data, we don't want to do any gradient, right? And we are fine. So for the accuracy, now, after our prediction, we want to, compare, we want to know the number of predictions that are correct, right? So we just do this equal to, so just to explain this line. So imagine our model predicts imagine our model predicts 1, 0, 2, 3. And the target, that is our original label, is let's say it's 1, 3, 1, 3, 3, or let's say 2. So now what we want to do is, so just imagine, like we are just imagining that our model outputs this, like as a prediction, right? And what we find here is just maybe for one, this is 1, 2, 3, 4, for 4 images, for 4 training examples. And the model predicts output. This is the model output, but this is the original, the correct label, 1, 0, 3, 3. Obviously, it looks like it has misclassified 2 as 3. But let's check. Let's see. So when you do something like this, what do you have? Now, it will start doing, it will start to do it start to compare element-wise, is 1 equal to 1? It says true. Is 0 equal to 0? It says true. Is 2 equal to 3? It says false. Is 3 equal to 3? It says false, right? And we want to get the sum because, we want to use that to calculate the accuracy, because the accuracy here will just be like 3/4, right? So if you take the sum, then it's going to output 3. What it means is that the model, was able to predict 3 correctly, which, as you can see here, this guy was the only wrong prediction. So, but this one, it's the same. So this is what just this line is doing, right? And it's going to return the sum. So here we call the accuracy here because during the loop, we need the correct training prediction. So here we want to save our model because we want to check if the last validation loss equals to the, if the current validation loss equals or which is less or equal to the last one. We always want it to be less, right? So if yes, then, return this and we want to save our model. So we want to keep track of our model. We don't want to lose the model with the best performance, right? And this is what this class will do, as you can see. It saves the model if the validation loss has decreased. And the fit function is just the loop, right? Because we want to just, run this in iterative way, right? And, the number of epochs is number of iterations. We set all of this, the training loss to 0 because we also want to keep track the validation loss. We set the number of correct train predictions and the number of test predictions. And as you can see, the train loader, remember, the train loader is what we define up. So it's just going to be loading 64 images, one at a time, right? So if we have 60,000, we will have 937, of this, right, in one forward pass. And as you can see, it's going to, what's just going to do is to, get the prediction, the loss, and the output. The train model is this method here that we have written. So it will just output the total loss and the output, right? The output is they are just the raw logits from the model, right? And basically, what we want to do, with the logit is to calculate the the accuracy. And in the accuracy here, as you can see, we just take the max because it doesn't matter whether it is a logit or not. At the end of the day, the largest number, we always take the largest probability, so it doesn't matter. And basically, that is what that is what you see in all of this, and we just try to get the loss for each of the training loader, right? And that's just it. So we try to print at every here. We try to print at, so I define 50 epoch here, and we want to print our result. Yes, for every epoch, we want to print our result. And here we check the early stopping because we want to ensure that the loss is always less than like 5 times. We have to wait 5 times. I can see I put a patience of 5. If you have done 5 times and you don't improve, just stop. And yes, so that's just it. And if I run my model, I run my number of epoch, that is the number of forward, backward, 50 times. And I define a patience of 5. And I just call my trainer. This is my trainer class here. It takes in the model, the criterion, which is the loss function, the optimizer, and the device, which is the CUDA. So once I do that here, the model and okay, train loader is not defined. Did I miss? Did I not run it? Okay. I think I ran it. Okay, yeah. So I'm going to rerun. Yeah, so I don't have much time, but yes, so now I can run my model. Yes, so now the model is running, and as you can see, it gives updates, and we see. So while this is running, I would be showing us, as it's updating. This here is just a function to show. I've run the whole thing, and just to see how the loss, you can see the training loss, it starts from here, and think about the training loss as this, as this hill, right? We want to tune the parameter such that the loss would be decreasing, right? I think that's just the basic idea. And as you can see, in the first pass, the validation accuracy was 94.18. The next one is 96, and it's improving. As you can see, the loss is decreasing, and I'm also keeping track. I'm saving the model. And yeah, so basically, as you can see, the training, the validation, you see the loss. We want to ensure that the loss is decreasing. And for the accuracy, which is between 0 and 1, and that is 0 and 100%. So here you can just multiply by 100. If in this accuracy, I think I multiplied by 100. But how come I'm saying 0.98? Okay, I think this is just the one I was printing. I multiplied it by 100, but in the one I was saving, that is this accuracy here, I didn't save it. Here you can see, I just appended the train accuracy without multiplying by 100. Well, it doesn't matter. It's just almost, yeah. So yeah, it's still running. As you can see, 97%. Yeah, so while it continues to run, so now if you look at the validation loss, the model would keep track. Anytime it improves, you can see it's going to be saving the model. And this is because I try to ask, it keeps record of the last validation loss, right? And the current validation loss. So it stores it as the minimum. So if the next validation loss is less than the one we have stored, then it's good, because we want to save the one with, that is actually with the decreasing loss, right? And that's just basically why you see that here. As you can see now, between the 9th and 10th, between the 8th and 9th, oh no, sorry, 9 and 10. Is it 9 and 10? Okay, 8. So after the 9th epoch, that is the 9th iteration, we notice that this loss here, the one that we stored last, just decreased. You can see 0.0888, now 0.0820. And you can see the accuracy is, is doing well. And now you can see from between 10 and 13, there is no improvement. If it gets to 14 or so, I think that would be a patience of 5. 1, 2, 3, 4. Okay, this is still 4. If it doesn't improve, it's going to stop, and it's going to, alert that, okay, early stopping. I've done 5 iterations, like, forward, backward pass, and there was no improvement. That is, this 0.0820 doesn't improve. And then I can just select the model. Now I can plot our accuracy. Yeah, so as you can see the loss and the accuracy, right? So the model looks good because we can see the loss is relatively close to 0, because that is what we want, because it's we want to minimize the loss. This is a minimization problem. And what we do here is, so they are just a bunch of codes too, but you can also have a look. I also wrote, I explained every line, and what we are just doing is we want to see the prediction. How does the model predict? Like, so what is so, so what exactly is the model doing? Now, I give an example. So this is our test set, which is the unseen data. This is 4. Our model predicts 4, and the true value is 4. And this, I try to show the probability distribution of how the model, assigns probability to each of the classes. We have 0 to 9, right? As you can see, it gives number 4 the highest probability, and that is why it outputs 4. Here, it gives In fact, it is just probability of 1. Here it's 0.94, but it's still fine because 0.94 is the maximum probability. Here it's able to predict 99%, 8, 3, 99, 1, 93. Here it gives 0.03, but 7, 93. Here 1. Here 1. Here 1. Correct. I think it basically, yeah, we find perfect predictions, I must tell you. But let me check if I can modify the code. Okay, yeah, I just try to specify. Okay, let me specify, this is 10 to 25. Probably I should specify 15. Let me see if there is, if there was a time where we had, wrong prediction. So let's do 25 to 40. Let's see if there was a place where the model, good. I cite one now. Very good. Now, there's a problem here. The model predicts 6, but the actual value is 5. So the model was confused. Yeah, because if you look at this number, it looks like 6 actually, but the prediction is 5. Well, you won't blame the model because, somehow it has learned patterns, right? And, it says, okay, and as you can see, it tries to, give number 5, like, excuse me, please. It tries to give number 5 probability of 0.12. Whereas it gives 6 the highest probability. If there are questions, please, you can ask. Okay, now that is that. Let us proceed. Now the question is, can we do better? And basically, what we always want to do is, oh, what is this? Okay, I tried to write a function to show us the confusion metrics. Usually that's what we have always done. So we want to see, how well the model, want to see. And here we can see the true label at this side, and we see the predicted label. Well, there are times the model wrong, like now here it says it predicts 6, but the actual number is 0. So it does this 13 times. So this is a wrong classification. Someone said, I don't quite understand the use of 784. Is it peculiar to this example? No, it is not peculiar. It is only peculiar because of our model architecture. That's the problem. So our model architecture is built linearly. It's not built to accommodate grid-like data, like images. So we want to ensure that we treat this image like a normal, data set, like, feature. In this case, we are just having like 784 features. Right? Just think about the last time when we worked on, this tumor, where we had 30 features, right? But in this case, now we're having 784, right? So that's what it means. Well, I'm still going to show us where we are going to use CNN. So CNN is convolutional neural network, and it handles grid-like images. So yeah, you can see here it makes a mistake, which is also expected. I think that's the only place it makes mistake, but it's quite interesting that you see that even model cannot be 100% perfect. And I can also tell you that if you ask me what's this number, I will start asking myself, is this a 5 or 6? So it's something that can lead to normal confusion. Can you omit the output prediction if it is less than 90%, or can you filter less than? Yeah, well, and if I would understand, can you omit the output prediction if it is less than 90%? Well, we don't want to omit anything. Or can you filter out prediction less than for reevaluation? Well, 90% is a huge number. Why should we filter all the, do you mean filter all the predict? Okay, 90%, okay, I understand. Okay, like these other ones are where, was very high, like 1, but this is 88. I think I think 90% is relatively high, but as you can see, this is 95, this is 1, this is 99. Well, I cannot really say if we would want to, filter out those that are less. So it depends on the problem statement. If you want to be 95% sure or 90% sure, then you can do what you can do what you have just asked. Like this is 88. And if you look at, it happens to be the least probability. And this is because the model itself is confused. It cannot really say if this is a 5 or a 6, which is even normal. Even as human, we can also make this mistake. But the question is, can we improve on our architecture? And this is where the hyperparameter tuning regularization comes in. And I still use the same architecture. I must tell you, I didn't change anything. But now I just introduced dropout and batch norm. So these are also, there are also techniques to keep, the model, it tries to ensure that during the training, the model, doesn't go far away from, what it should be. For example, if you look at the initialization of the weights, these weights are, they are randomized and they are sampled from, standard Gaussian. And, when we start, doing this linear operation and things like that, it's possible that, the output begins to, deviate. For example, you can, the variance per se would, begin to, go far from what you would expect. Like, you have standard deviation 0, but a variance of 1, right? Or a standard deviation of 1. And, and you carry out a linear operation and, the variance just overshoots to something like 5. And then the model is not stable. So what we want to do is, here we batch norm. Batch norm means for each of the batches, we are going to normalize. Remember when we started, before we fed the image, the images into this neural network, we normalized the, we normalized the images. But along the line, so this batch norm, what it will do is to ensure that after each of the hidden layers, or after each layer, it's going to do a normalization. So when we get this output, it's going to normalize it. So it's still going to center it with mean 0 and some standard deviation. And so that is what the batch normalization is, and it's going to do it in batches, where they are also quite sophisticated technique, as this batch norm is also very tricky. We have the group norm, we have the instance norm. We also have you can read about it, and we have the dropout. So what the dropout would do is, now think about this neural network now. Now, during the forward pass, dropout will say, okay, yeah, I have 1, 2, 3, 4, 5. I just want to randomly drop some nodes. I want to kill some nodes because somehow, I don't want to, how can I say, so I don't want the network to be built in such a way that, it will be reliant on, a particular set of nodes, right? A particular set of neurons. And what dropout will do is, in the forward pass, this guy can be very relevant. But in the second pass, what if I try to shift this, relevance to another node and I just kill this? And that is what dropout would do. So I want to drop 2% of this, the nodes, the neurons. And, when you say 2%, on average, it's going to drop, like, for example, if this 1, 2, 3, 4, 5, is going to drop 2% of 5, right? And so you begin to see that the network itself, the neurons will be fighting for relevance. And yeah, in that case, we really expect that at the end of the day, we want, if we are doing this dropout, if, the neurons that will be responsible for firing or for, extracting this high-level feature, would be kind of competing. And in a way, it has to settle, it has to settle somehow at some point. And, so that we don't, kind of, push the model in the direction of, just focusing on a set of nodes. It's just like you want to assign task. Today you want to give this task to this person. Tomorrow you want to give this task to another person. You want to make all of them you want to, how can I say? It's just like you want to ensure all of them are active. Some nodes are not always active. But when you begin to do this dropout, then all of them begin to, become active. And like today now, this guy is relevant. Tomorrow, please don't just stay aside. let me focus on some others. And that is what the dropout will do. And I just implemented that, nothing more. After before I call the ReLU, our activation function, right? What I just do is to normalize it, right? Then I call the activation function and I do the dropout. And if we do this, let me be consistent. Oh, I think, no, let me stop. So what I did was to just do the same thing. And because now we have a new model, we have to put the model parameters into our optimizer, right? Because the last one was another architecture. So now let's run our model. And this is another, let's see if it's going to improve, because in this case, we see that even the best loss was 0.820 with an accuracy of 97.82. So let's see if this would even perform better. So we'll keep track. So while it's running also, because we have saved our best model, we have to call it, right? And, we also plot the confusion matrix. But let's see, let's try to see if the loss would improve. This is 0.0921. Let's see, this is 0.0820. It's still running anyway. Let's see if it's going to improve, at least. Oh, good. Now we see that the loss is now 0.0708. But if we compare it to the best loss here, you can see the model has improved. So there are ways you can improve your model, and you can read on regularization techniques, hyperparameter tuning. You can always improve by adding this dropout, batch normalization. You can also read on other types of normalization. Sometimes you don't want to normalize by batch because of this data. There will be a kind of how can I say, because because when we are normalizing, right, we want to normalize with some parameters like the standard deviation and the mean, and this can differ. This can differ depending on the batch, right? Because these are batches. We don't know how far the next batch would be from the previous batch, and there's always a problem because if you're normalizing, you want to ensure that you are consistent. Like you want to use just one parameter to normalize, and for each of these batches, we see that these means and standard deviation will just be shaking. It will be fluctuating, and the idea is to use some techniques, right? And yeah, so batch norm is okay. At this level, it's not bad because we're using a batch size of 64. But if you're using smaller batch size, probably you might want to check another technique like the group norm or instance norm. There are also other normalization. Well, it looks like even this improved architecture is doing better because our loss even is as far low as 0.05. So I expect this to be better, right? But we are still waiting while it's running because we put a patience of 5 and it looks good. And if you plot I've done this before, but if you notice in this last example, there was a particular place like this 0 prediction. The model predicts 6, 0, 13 times. Please, can we mute that guy? But in this case, the model predicts, yeah, it accurately predicts, but let's run. I hope I'm able to reproduce this result, but it's running. While it's running, let's just keep our fingers crossed. As you can see, the validation accuracy even gets to 98%, but in this simple neural network we built, it never gets to 98. It stops at 97. So is our model done? Oh, okay. I think we have done 4 now. After the 5th one, if it doesn't improve, it's going to stop. I hope it improves or stop because of time. Okay, so while it's running, let me also run this. Yes, it stops. It doesn't improve. Now, so we can see now that, well, I was not able to improve, but there are cases where if you look at this table, for example, this 11, the model predicts 9. when the true label is 4. 11 times, wrong prediction. Let's check this one. 9, 4. Oh, this even is worse. Well, I think this 13 here, this 13, the model predicts 6 for 0, 13 times. But here, the model predicts 6 for 0, 4 times, which is quite minimal. And if you look at this diagonal, you will see their improvement, right? So this is 955. This is 970. So that means the model predicts 970 samples correctly. This is 1128. This is 1125. Well, not better. Let's continue. This is 999. And this is 1023, as you can see. Additional 24 correctly. This is 990. And this is 997. If you go down, you see an improvement. So now let's move to convolutional neural network. Well, I hope in the future, probably we can also organize trainings focused on computer vision. There we can talk extensively on, but I'm not going to say much. But the only difference now is we want to create this network such that it can handle a grid-like data, like the 2x. We don't have to, we don't have to flatten it like you mentioned. So what we can do is we will use the convolution, method from the neural network model. So it's called com2D. What it means is that we just want to feed in the image direct such that the weight we can, I think I talked about it also during the presentation yesterday. The weight will no longer be linear, right? It will be a kind of metrics. We randomize this matrix weight called the kernel, right? And we try to stride it along this two-dimensional image, right? So what it will do is if this is our image, we have, let's say, a 3x3 matrix. It's a weight matrix, and each of the metrics also has its own bias. But the only difference now is that the weight is not a scalar like the linear. It's a matrix, and it strides 3x3, 3x3. It goes like that, sideways, 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 sideways. So that's the only difference. And it performs this product, this linear operation element-wise. The 3x3 matrix, it picks the first 3x3 pixel in the image, then here. So that's just basically it. And here now the number of channels now, we have one channel, which is the image, is one channel. Now we output just like how the linear layer would output, maybe like, for example, 256 as we did the last time. Now we are going to output, 32 of these weight metrics, right? Because of course we are not working with vector, like just vector of matrix, like how can I say, like this weight, like just think about these layers, just one vector, and each value is just represent the node. Now we have metrics like this one. Now will not be a scalar; it's going to be a matrix. Right? So we are going to have 32 of these, and the 32. Remember, the output of one would be the input of one. So next one will be 64. So here we just do a simple, we just do two convolution blocks where we have 32 and 64, feature maps, and we do the dropout like I explained the last time, right? We apply this 2D dropout. So what this 2D dropout, it operates over the 2D input. You understand, in an identical manner across the channels, right? Because we are working with weight metrics. We are working with channels now, not, not just a scalar without a channel. So what it's going to do is it's going to drop, like now this 32 now, remember, like I said, it's 32 feature maps. So it's going to drop 25% with probability of 25%. So it's going to drop some. So just think about, we are going to drop 25% of, each of these feature maps. And we just do the same thing. We do a max pool. A max pool also is just what we try to do is we get the maximum between, and so we select also, we look at the image, the output, and, in this matrix-wise, we try to just pick the maximum. So we can define, the kernel size too. So if you pick 3 by 3, it goes to the first 3 by 3 in the image, then it picks the maximum. It moves to the next 3 by 3, picks the maximum. If you choose 4 by 4, it picks the first 4 by 4. And there we can also run our model. So let's see if it's even going to improve, because here the last part was 98%, and the next part was, the first network was 97. The loss, this was 0. The best loss was 0.08, and the best loss here was 0.05. Let's see if the convolutional neural network would improve. We already have 0.05 at the first start, which is even quite close. Oh, 0.0525. This is, this is already 0.03. Wow, this does well. So let me check if this, I want to see if this one would, if it will do this, if it will actually, give us the correct prediction here. I want to be sure 25 to 40. So I want to do the same here. 25 to 40. 25 to 40. So the model is still training, as you can see. It's doing well. The loss is decreasing, significantly, better than even the last, the last one, 0.05. Oh, yes, 0.05. And mind you, we are not using the training loss. We are using the validation loss, because we are testing our model on the unseen data, not on the training data. So be careful. You cannot use your training loss to determine how good your model is. You have to use an unseen data, which is the validation loss. Okay, our model is still training. Yes. Oh, nice. We have gotten to 99, something that was never achieved. Yeah, the best was 98. And in the simple neural network, the first neural network without the regularization, the best was 97%, which looks good. The model is doing well. And when we are done, we run the confusion metrics, even though I've tried to run it before. Okay, now while our model is training, and we are waiting, now I try to, all along we have been building this model, and the question is, how do we deploy our app? How do we deploy it as, as an application? So think about, okay, you want to build a web app. We talked about that yesterday. And so while it's loading, right, let's, I just did a simple, web application using Flask, right? So basically, Flask is also a web, is a framework. It's a web framework for, that works on Python, right? Just like us, we have, normal JavaScript, but, this is, the Flask itself, sorry, here, so I won't talk about this much because of time, but what we want to have is we want to just write some Python code. So here we'll import the Flask, as you can see, from Flask, import the Flask. And Flask is just like, it's just it's a smaller version. It's just it's a simpler micro version of Django. Yeah, so if you're familiar with Django, fine. Flask is just a kind of micro version of Django, so it's easy. And you can see I downloaded the model we trained from here. It was not any magic. So remember that we were saving our model here. You can see, no, not here. In the training loop, we try to save the model here. Where is it? Yes, here. And as you can see to the left, you see the model here. So I just downloaded that. So you can download it on your local machine. So let's see. Oh, this one is still training. Well, while it's training, let me just talk about the Django. So just assume that we have downloaded our model. We want to create a web application. So this is just some simple Python script. So we have to specify the path to the model because we want to load the model, right? And, we also do the same, transformation. Remember, we transformed the data. If you look at where we started, we did a transformation. So we have to be consistent. Otherwise, as you can see, we did a transformation. So, we also want to do the same transformation. So we want to, transform. And I just wrote this bunch of script. It takes a request method post, which we will see on the web application on the website now. It's just running locally anyway. I didn't host it. And, it grabs the image, right? It opens it. So when we upload an image, we save it in a folder. Then we convert it to grayscale, we transform it, we unsqueeze it. So we want to add the batch dimension. Remember I told you that our neural network takes batch size, right? Channel, height, and width, right? And what we have is just this, because of course the image is just the channel, height, and width. So we want to add an extra batch size, otherwise it will throw an error. So we want to unsqueeze. So what we do, we just try to add one more dimension. So if our image was 12828 before, it's now going to be 12828. And we call our model here net. So our model has been, so this model is the convolution. I noticed the convolution, it turns out to be, it performs better. And this is because of, as you can see, you can see it performs better. Very possible. So let us try to run. Let's see if this prediction would, let's see that point where this first model, get this one wrong. I think 1, 2, 3, the third prediction. Let's go to the third prediction. 1, 2, 3. So you see, in the first model, where this where we use the simple neural network, without the convolutional neural network, you notice that the model predicted 6 for this particular sample, but now it does the right thing. And the model is more robust, and this was what I downloaded, and I can even show you. So I can also re-download it. So you can just click on the file, you download. And, I can download it to, it's going to load because the model is not something very light, right? And, so it's going to load. Then, while it's loading, let's just wait for a moment. You download it, but I'm going to send all the whole file, and I'm going to do a description of how you can run, it locally on your machine. So now it's, yes, so I can just quickly undigit so you can see I can overwrite it, so nothing much. So now we are done. So let us deploy our app. So we have to, because when we are calling our model here, we need to, remember this is the diction. So we have stored all the weight, the model weight. Remember, the weight is the most important thing during the training, the weight. So here we are going to load it. So we are going to load the weight just by specifying the path. The path already is what you see here, model. So here. So once we load it, we put it in evaluation mode. Remember, we just want to evaluate. Then with the touch no grad, it means that we don't want to update any gradient. Then we run the output. Here we get the probability. Here we get the, we try to get the maximum, right? The maximum probability and the index, which is just the number. And we try to send it, we try to render it to the web page. So I will run my Python app.py. So while this is running, yes, so on our web application, I would copy, I will copy the IP. Yeah, so I just wrote this simple code. Yeah, so it's nothing fancy. So I wrote an image in my tab. As you can see the tablet here, I used my tablet. And why I chose black background was because if you look at the image we trained, the image was on black background. So you have to be careful. Well, I tried to just use white background. I noticed that the model was just misbehaving. And this is because, models are quite sensitive to colors, and all the images are, all centered around black, just all black. And if you try to write this on a white, sheet, there might be problems somehow, in how the model would interpret, right? Because here we just have white and black. So what it means is that here we would have, pixel values more active here than these other sides. But if we have white and black, it will be the reverse. So there might be problems. So you can actually train both. If I were you, I can just, I can write this digit on a white background also, and I combine both, and the model can train. I mean, the model can learn how to, so that when it sees something on white background, it doesn't just, yeah, so I did that, and what I just did was to crop, each of the images, and you can see 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So let us predict this image. So let us use our web application that we created. So we have the handwritten digit classification. So once I'm here, I'm just going to choose the digit, what I wrote with my own hands, not with the data we downloaded. And once I click on classify, so what would happen is in the HTML file, once I click on classify here, that is what you see here, it is going to send this post request, right? And, it's just, we are going to grab it here, as you can see. So we grab the file and we do the prediction. And once I click predict, oh, perfect. So our model predicts 0 with the probability of 99, of course, like just between 0 and 1 anyway. So let us predict 1. Our model predicts 1. I mean, these are my own handwritten digits, not the test data set. I mean, not even the validation we used for the, for the data. For 2, this is 2, 99%, good. For 3, wow, good, 99%. For 4, oh, this one messes up. Oh, it says 7. It doesn't get this. Okay, I don't know why. Maybe it's somehow it's trying to, it looks like it's interpreting this as 7. Okay, let's choose 5. Oh, this is correct, good. Let's choose 6. Oh, perfect. Let's choose 7. Oh, good. Let's choose 8. Oh, 8. Oh, perfect. Okay, let's choose 9. Actually, I never tried this because wow. So we are done. So I think the model only misclassified this 4 as 7. That's the only mistake. And it even assigns 98%. Well, it might be that we can improve on, on our model. And let's see if there's a case where the model predicts, because the model is predicting 7 and the actual value is 4. Let's see if there was a time where it actually messes 7, 4. Oh, in this place, it doesn't misclassify. Then I wonder why it well, maybe, let's try to view some of the image. Let's see for 4. Maybe I wrote the 4 in the wrong way. Somehow, people write things differently and you never can tell. Yeah, because this 4 looks strange to me, how someone writes 4 like this. Normally it's supposed to cross. Yeah, but this is also good. Well, yeah, I mean, it's one of those things, but as you can see, out of the 10 digits I wrote with my hands, it's able to, classify 9, 0, 1, 2, 3, 5, 6, 7, 8, 9 correctly. So which is not bad because we don't expect 100% because even the accuracy here is not 100%. So as you can see, it's 99%. So which means that there is this 1% that might be an offset. So which in this case,
exactly.
Yeah, thank you. So I mean, because we're not.
I just wanted to comment on that, Dr. Austin.
Okay.
I think the model is doing very well at the moment, right? because
Yes,
the
yes.
4 looks like 7. If you see the
Yes.
distance where you had the cross is
Yes.
towards the top.
Yes.
So the
Yes.
model would have, you looking at the patterns in 7, that's almost looking like a pattern of 7. So
Yes.
probably that's why the model misclassified it. And then if we look at the training samples of 7, we will
Yes.
see much of 7 that are looking like this 4.
Like 4. Yes,
And
perfect.
if you look at the training samples of the 4, we may not have representations that look like this 4.
Yes, exactly.
So no model is ever 100% perfect.
Yes, yes,
So
perfect.
but it misclassifying it as 7 makes sense. If it misclassifies it as 0, then you know
Yes,
the
that's the
model is
problem.
hallucinating.
Yes,
But
yes,
if it
yes,
misclassifies it as 7 and you can see 7 in this 4,
yes,
you can
yes,
actually see 7 in this 4. So it shows that the model is not hallucinating.
yes,
Probably we can improve the training accuracy by
yes.
supplying more examples of
Exactly,
4
that looks
that
like
are
this.
like that.
Yes,
Exactly. And then the model will be able to now learn that
yes,
representation well.
yes. Just like this too, where this model, misclassified this. So it's something that,
Yeah.
yeah. So I think I'm done for today. And, this is just a web application where I just wrote myself on my machine. And, I can even host this and you can play around with this. So aside from the fact that, you want to also build models, like, you want to create a kind of, smart, smart systems that can do something, then you can think about, okay, in the future, if you are going deep into, machine learning, deep learning, or even in the areas of natural language processing or computer vision, you can do nice projects and you can host your project and, you can even put it on your GitHub. And, even this is a personal project. I'm also going to send an assignment, and this is called the fashion. It's called the fashion MNIST. It's called the fashion MNIST. And this one, you would create a model that can classify, images that, fashion, like clothes, as you can see. Oh, not here. Let me put the image here. And as you can see, so you want your model to predict. I'm going to leave this as an assignment. You can use the same code, just ensure that you are loading the correct image. The code will work regardless, but we have to be careful because now these are not numbers. So I'm going to also explain in details how you can, because the model cannot predict this, t-shirt. So you can just assign them to labels like ankle boot would be 0. And once it outputs this number, right, this index, then you can just index, And if you have questions, you can ask. Today is the last day of this, section. Next week will just be on Power BI. So maybe for the next 5 to 10 minutes, if you have questions, I'll be happy to answer. So I don't know if there is something else you would want me to talk about or briefly explain. For the code, it takes time. You would have to go through the codes one step at a time. I would also try to, what I would do is in this trainer, I would try to add more comments to each lines. So before I send the code, so that you would understand what every line of code is doing. I hope we enjoyed the project, and I'm sure that we also like how we deployed our model to the web as a web application. Can you train the code on a grip? Yeah, you can. You can train. I mean, because what we just, the data we worked with was just on black background. So I can decide, because most times it's weird to see a white background, right? Like unless, because I was able to write these images on my tablet. If you have an A4 paper or a white paper, it will be a white background, and there might be problems. So you might want to, combine this, black, green background. I mean, you can even combine all the color background so that your model would be very robust, so that you won't train it on all black and it sees green and it's going to be confused, right? So the essence of training model is to represent reality, right? And in a more diverse way, you want your data set to be very diverse. I can tell you this data we used was not diverse because it only focuses on black background, and it's going to be biased towards black background. You can try to to write the digit on white background, I can tell you the model will just misbehave. Okay, I'm going to send the script, everything, so that we can also play with. If you like the project, please comment on the chat, say, yes, I like it. And there are also lots of interesting projects on computer vision that you can do. From time to time, we keep enjoying, we keep talking about enjoying doing projects together and things like that. So if there are no questions, I think I would end this class today, and I'll give an assignment. You would have to build a machine learning model that can do this prediction. I'm going to put a guide. In fact, I can even send. I will keep you updated on WhatsApp. And let me end this section. And let me stop sharing.
I just wanted to say something. I don't know if everybody, those in this class, can we just put our hands and clap at least for our teacher, Dr. Austin? Just put on the chat box, thank you, because I'm currently at the airport, flying to another country, but I've been enjoying the class myself. I've learned a lot even by listening to this. So thank you so much, Dr. Austin. It's been reminding.